This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hello and welcome to another episode of Design Safe Radio. I'm your host, Dan Zahner. Super excited to be with you once again and talking to a colleague of mine that I haven't had the privilege of meeting yet, but I've been following along with her work for the past few years as she's part of the Tallwood team that has been working on this amazing project we can't wait to tell you about since at least before 2017 when they had the first edition of Tallwood out at the UC San Diego Shake Table, where my friend Keri Ryan is at today. Keri, it's nice to meet you.
Nice to meet you.
So tell us a little bit about yourself and your research. It's just really cool what you guys are doing down there.
Yes, I am a professor of civil and environmental engineering at University of Nevada, Reno. I have been at UNR for 12 years, and I have been doing seismic engineering type of research my whole career. I sort of had my roots with seismic isolation, which is a type of protective system that's very good at protecting buildings and bridges and infrastructure from the effects of earthquake. I've kind of expanded out more recently with a focus on non-structural components, which I think in many ways is not unrelated to the original field of seismic isolation. So I am really excited to be part of the Tallwood team. And we have been planning this test, intensely planning for the last 2 years. So it's really exciting to see it come together.
Yeah, the Tallwood test is just unlike anything I've ever seen. I mean, it's a full-scale building in a way that, like, you know, from a not a structural engineer person who's not familiar with this way of seismically isolated buildings, it looks incredible. And from the first small scale test, this one I think is going to be really amazing. So can you tell us a little bit about the NHERI Tallwood project? This is a huge team working on a huge we keep using the word huge, but there's just not another word for it.
Yes, it's a large team. There's a lot of people involved. The overall scope of the project, we are constructing on the seismic shake table at UCSD. We are constructing a 10-story Tallwood building made of mass timber components. And so what we mean by mass timber is like engineered lumber, large beams, large panels that are engineered to have specific properties for different actions. And we can only go so tall with typical light frame wood systems because you just can't get enough strength and resistance. So mass timber allows us to go taller with wood. One set of rocking walls is built with mass plywood panels. And so, just think about different plywood strips, I guess, glued together, etc. When we originally started this project, our vision was cross-laminated timber. Cross-laminated timber are boards that are basically, like, I have a visual.
Excellent. Love visuals.
Here is a visual of a mass timber panel and how it's built. So it's boards aligned in one direction and glued together, and then the next layer aligned in the other direction and glued together. And the neat thing about CLT is it gives you kind of resistance in both directions. Mm-hmm. So that was our vision, that we would use primarily CLT in the building. At the end of the day, CLT is more expensive, and we had a harder time getting the donations. We got donations from a lot of different vendors, different products. So we are using not only CLT, but the mass plywood panels. We have one set of rocking walls is CLT, one set of rocking walls is the plywood panels.
Oh, interesting.
Yeah, I have another visual also for floor systems.
Oh, cool.
Okay, so we have in the floors of the building 4 different types of floor panels. CLT by Mass Timber Services, glue laminated timber by Mass Timber Services. Glue laminated timber, from what I understand, is like a two by whatever that are oriented vertically and glued together. That's the GLT.
Okay.
Nail laminated timber, dowel laminated timber are the same, except the boards are nailed together or connected and fastened with dowels, like shown here. And then the last is veneer laminated timber by Boise Cascade, the top 4 stories. And that's like a plywood, massive plywood panel. Again,
Yeah,
I think is the best
just
way to
a
describe
whole lot of veneer glued together.
Yeah.
And these floors are how thick are these floor panels?
Depends. They're varying thicknesses. They start at around 6 inches, 6 to
Wow.
8 to 10, I believe. Yeah.
Yeah, just to kind of give a
Yeah.
sense of scale, because the scale model gives you this idea that, oh yeah, it's this small thing, but it's a building. So normally this would be poured concrete, right? Like 4 to 6 inches of poured concrete or something.
Right. Yes.
Huge
And normally I think you would still have a topping layer of gypcrete or something like that. Ours is pure wood, and you can almost see from this this diagram here, there's little straps across all the floor panels to because they're manufactured, and then the straps are used to collect them and transfer the loads so that they can function as a diaphragm. And every type of floor system that we have here has different strapping details. When we walk through the building, those aren't going to go away. You have to kind of watch your step because there's these straps. Yeah. So in a real building, you'd have to do something to finish the floor, but ours is going to be a little bare. And we can see what happens.
But yeah, it makes it so you can see what happens and also disassemble it at the end a little bit easier.
Right. So I think we should backtrack, and I want to talk about the overall concept of.
Yes. Yeah, we've gotten a little bit down a rabbit hole because this is so exciting, which we tend to do, right? So as we're backtracking, so this is all from a whole lot of partnerships all together in just this Tallwood idea. So yeah, let's backtrack to there. There we go.
I explain the overall concept of what we're trying to achieve with the test. So the main goal of the test is to develop and validate a new type of lateral system. And what we mean by lateral system, the way that the structure resists the earthquake from lateral loads, wind and seismic. So ours is the wood panels are designed to be a rocking wall system. They are not fixed to the base. They are designed to rock up off the base. And I mean, that's good because they naturally want to, and the rocking motion allows the movement to be accommodated without damage. But in order to support that rocking motion, there's several details that are important. The entire walls are post-tensioned from the base all the way to the top, post-tensioning strands. And when it rocks up, they provide like a restoring force to help it keep it from totally rocking over. Wow. Also, another detail that we see. So first of all, you either have a set of coupled rocking walls, like in the 2-story building that you recalled from a couple years ago. There were 2 sets of walls that were kind of connected together. We opted for bounding columns. And yeah, so you can see there's the rocking wall panels and the bounding columns. And connected between the rocking wall and the bounding columns are these UFPs, U-shaped flexural plates. So as the whole system rocks, those plates deform and dissipate energy. And dissipation of that energy helps to limit the overall movement of the building. And then the last piece is the way that that the wall is connected into the diaphragm. And this shows, hopefully you can see or understand this graphic. Floor panels connected into the wall system. We call it a shear key, but it's fastened in like this a lot of steel hardware. Okay, this massive steel plate with a extender beam, the beam is extended through a slot in the hole of the wall. So it allows the wall to rock up without taking the floor with it. And that's good because if the floor, rocked up with the wall, then it would be subjected to this distortion and so on. It would get damaged.
Right.
So this connection here is carefully designed to prevent that from happening.
Wow. So you've got that going on for 10 full stories. That is just bonkers.
Yeah. It's a lot of steel hardware, a lot of detailing too.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation, grant number 2129782. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so that we can improve the show and also help others find our episodes in iTunes. Thanks for your feedback and support. We really appreciate it. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.